Hey everybody. So today we're doing section 9.3, moving right along. I told you this whole chapter was about functions and inverse functions. And in particular, we were going to eventually get to two special functions, okay? We're going to get to the first one today. It's called an exponential function. It's one we haven't studied yet. We've studied polynomials and radical functions and rational functions. So this is the first time we've looked at exponential functions. Okay. And so the first question I kind of expect you to have is, well, what is an exponential function? They're functions written like this. Some number raised to the x power. So for example, this b here, this is the textbook kind of way of writing it, b to the x. Something like this. F of x is, somebody shout out a number. Okay, sure, 7 to the x. Or it doesn't really matter. It could be 1/5 raised to the x power. What makes this different than all the things we've done before is that notice the variable is in the exponent. We've had exponents before, but they have been numbers, not our x. So that's what that kind of makes these different, a different animal kind of special. They give it interesting characteristics. Okay? So that's what an exponential function is. Is this something we have a base raised to the x? As long as this is not 1 or 0, then it's interesting. If it's any other number, it's interesting. Okay, so first let's kind of explore the graphs. That's the first place we're going to go to see what they look like. But then how are we going to actually graph these things? Well, how have we graphed pretty much everything in this class? We've graphed it with a table of values. So you'll pick some x's this time. There's nothing fancy to this. You choose some x's. Plug them in, and create your table. Okay, so I'm going to do two examples with you to be able to compare these graphs. So this one is f of 2 to the x. Okay, and so I'll pick some x values. X, y, I don't need too many. 4 or 5 will be enough to get the shape of this. Let's pick some negatives. Oh, let's see. It's a good negative here. Negative 2, negative 1. We'll pick 0, 1, 2. I'm going to pick a lot just to show you the shape, but you could probably get away with 5 or so, and I will be happy. I'm going to pick 4. So let's see. We could probably do some of these in our head. Like if I plug 0 in, 2 to the 0. Remember, anything to the 0th power is equal to 1. So this output is 1. To the first power, I can do that one without a calculator. 2 to the 1, what's that going to be? Well, that's just 2, right? 2 to the second power, I can do that one too. 2 to the second power, 2 squared is 4. Let's see, can you do 2 to the 8th? Or, sorry, 2 to the 3rd, I gave it away. 2 to the 3rd is 8. Okay. Let's see, 2 to the negative 1. Can we handle that one? 2 to the negative 1. Remember, a negative exponent would mean that we'd need to put it down here on the bottom. 2 to the positive 1, which is just 1/2. 1/2. How about 2 to the negative 2? 2 to the negative 2 means we need to move it to the bottom. 2 to the 2. And that becomes 1/4. Okay, so these are fractions, but we can still graph them. We'll just not be perfectly exact. So let's graph these points. So my first point can be negative 2 and 1/4. Negative 2 and 1/4's barely above the line. Negative 1 and 1/2. That's halfway up. Getting a little bit higher. 0, 1. 1, 2. 2, 4. 3, 8. I believe that's 8. Man, this thing gets high really fast. I'll go ahead and tell you, if you were to do negative 3, it'd be even closer. What this thing does is it gets really extremely close to the x-axis, and then it shoots up really quickly. Something should sound familiar, like with my explanation of this, in the phrase exponential. This exponential function. Have you ever heard the phrase something grows exponentially? They're talking about exponential functions. And that's why they say this, because exponential functions have a tendency to shoot up really fast. They grow really quickly. This thing shot up and curved up very, very fast. If we In fact, if we were to go to 4, it would be off the graph already up here. Okay. The other things you need to notice about these graphs is that they have an asymptote. They'll have an asymptote that they will not cross. This one happens to be at 0 here, the x-axis. It will not go below it because there's no way for 2 to the anything to ever be negative. And it never can equal 0. It will get extremely close to 0. Okay? So these graphs are kind of shaped that way. Now, there's an interesting kind of another change to this graph that can occasionally happen. So it depends on what the base is raised to the exponent. And I got another base over here. I used a similar number. Instead of 2, I used a half. Okay? So we'll talk about these bases in a second. Let's graph this one. So we're going to do the same thing. We're going to make an XY table and just pick some X values and some Y values. It doesn't really matter. We could probably get away with it. We kind of know the shape now. Just -2, -1, 0, 1, and 2. So I'll do the easy ones first. So 1/2 to the 0th power. Remember, anything to the 0th power is going to be equal to 1. So I know that one. That one's the easy point. Anything to the 1st power is just going to be itself, right? So 1/2. Now, if we square a fraction, do you remember how to square the fraction? You square the top, you square the bottom. Well, what's 1 squared? It's just 1. 2 squared is 4. So this is 1/4. So wait, this looks kind of like this other graph, but upside down, doesn't it? Well, let's try -1. 1/2 to the -1. What happens with a negative exponent? That's going to flip this fraction to a 1, which is just 2. And if I did it to a -2, it would flip it 2/1, and I still have to square it then. That's just 4. Now, if you get all confused on all these exponent rules and everything, you can just use a calculator to type in exactly these pieces over here with parentheses. So be extremely careful with parentheses, and it will give you all these values. So let's plot this one and see what we get. We get, let's see, -2, 4. 1, 2, 3, 4. -1, 2. 0, 1. 1/2. 1/4. And if you did -3, do it for fun, you'll get 8. So this is actually almost the exact same graph, but it's kind of flipped backwards, isn't it? So have you ever heard of like exponential decay? This graph is decaying, and it drops off really quickly, and then it kind of levels out. So that's where those terms come from. The reason the word exponential is attached is that's the name of the function type. So now let's talk about these. They kind of look like, I guess the worst way to explain them is they kind of look like L's, right? And I know which way the L is going to be going depending on the base. Okay, so this base is 2, this base is 1/2. If this base is some sort of fraction or decimal in between 0 and 1, you're going to get this shape over here. Like 1/2 is between 0 and 1, 1/3, 1/4, 1/5. You're going to get this shape right in here. If it's bigger than 1, so I guess I could say greater than 1, you're going to get this exponential growth shape right here, okay? We'll talk more about that in the next section. We're going to dive more into exponential growth and decay next time. For now, we're just discovering how the graphs look and learning how to plot them, okay? So that's graphing them. Now the next topic we're going to dive into is solving equations, okay? And we're going to just dive into one technique today. We'll actually hit some other ways of solving these type of equations later in this chapter. But for today, it's actually pretty easy. If I can get the base of the left and the right side to be equal, then that must mean the exponents are equal. This one doesn't take any solving. But since these two sides are equal, if their base is equal, that must mean the exponent is equal. Okay, I did this really easy example just to kind of state the rule. So look over here. These two things are equal. Their bases are the same. That must mean the exponents are equal. So could I solve for x? Well, yeah, I could divide both sides by 2. And x will equal 4. So that's really simple. right? But what was nice about these two examples is they already had the same bases. So what happens if the base is not the same on each side? I give you one more where the base is the same. If the bases are the same and they're equal, that means the exponents have got to be equal. So I could solve this by subtracting 6 over x equals 4. Okay, so now finally what I was trying to say. What happens if the bases are not the same? Do y'all see this? Is there any way to get them both to have the same base? Well, I could try rewriting 16. Is there any way to write it as 2 to some power? And the answer is yeah, actually, 16 is 2 to the 4th, and you could just grab a calculator and try, okay, 2 squared, 2 to the 3rd, 2 to the 4th. Oh, look, I got 16. Okay, so that's awesome then, because I could rewrite 16 as 2 to the 4th. Now, let me ask you this. Do they have the same base now? Yes, they do, and they're equal. So what does that mean about the exponents? The exponents must be equal. So it wasn't too hard. And it just gets a little bit more, steps down one more time, okay? So what if I have to work to get the bases the same on both of them? So look at this. 25 is the base over here, 125. Can I get them both to the same base? Can I make this 25 to some power? And the answer is, well, I actually could, but that's it would be a fraction. I'd rather stick with whole number things. So can I make this something? And the answer is yeah, I could make 25. That's the same thing as 5 squared, right? And all of that, 25 is raised to the x power. So 5 squared with x. Can I rewrite 125 as 5 to some power? And the answer is yeah, it could be 5 to the 3rd. Now I'm going to go ahead and tell you to do this. It's going to take some guessing and checking unless you know your powers really well. Okay? If you don't know your bases and powers and exponents really well, you're going to have to guess and check. Okay, until you can find things to match them up with the same base. Alright, now let's take a look to clean this side up over here. 5 squared, what do? What's the rule when I have an exponent on the inside and an exponent on the outside? Oh yeah, they multiply. So this is just 5 to the 2x equals 5 to the 3. Okay, well the bases are the same, so then that means the exponents must be the same. 2x equals 3. So can I solve for x? You bet you. Just got to divide by 2 on both sides. X equals 3/2. And actually, if you remember, our chapter we did 2 chapters ago, if I took 125 and put it to the 3/2 power, that would actually equal 25. Remember, that would be like square rooting it, so you could, it's, take it to the 3rd power, then square root it, it would give you back 25. All right, awesome. So let's do one more over here. Can I get both of these to the same base? Can I get 8 to have a base of 4? And the answer is no. I know some of y'all are tempted to tell me 4 squared, but before you do that, what is 4 squared? It is 16. So I'm going to try to get them both to something. What about 2? Can I rewrite 4 as a base of 2 to the something? The answer is yeah, 2 squared. Can I rewrite 8 as 2 to the something? Yeah, 2 to the 3rd. So let's rewrite these. So 2 squared, that's 4, right? X, don't forget the x to x plus 3 that's floating out there, equals, what can 8 be? It can be 2 to the 3rd. Right, and it's got an x floating out there. So this just takes some guessing and checking and practicing. You will get a lot better at this. Okay, I know some of y'all are sitting there saying, man, he's coming up with these things. How? It just takes a little bit of thinking ahead. So now how do I clean these up? Remember, this 2 is going to be multiplied by x plus 3. So you may want parentheses there to be careful. So that'd be 2x plus 6. And this 3 is going to be multiplied by that. So 3x. So the bases are the same. What does that mean about the exponents? They also must be equal. So let's see here. I could subtract 2x over from this side. Oh, when I get really lucky, I don't even have to divide. 3x minus 2x is 1x, or just x. Okay. Are there any questions on the solving? The solving's a little bit weird, but you'll get used to it. We'll practice a little bit. I'm sending you a worksheet. Make sure you do try the worksheet, okay? And then the answers are attached. So there's only one more topic in this section I want to cover, and it's actually one that you've done in Math 105 last semester if you took 105. It's those interest and rate problems, compound interest problems. These are actually exponential problems as well, okay? So we're going to give you the formula so you don't have to memorize it. The formula is given right there. Oops, I can't draw a straight line. Try again. Formula's drawn right there, given to you, and I've defined all the pieces for you right here if you need them. Okay, A is going to be the final amount. P is the principal, but most people don't know what principal means. That's the beginning amount. R is the rate, but here's the hint. You got to change it to a decimal. N is the number of times compounded a year, and T is time in years. So let's see if we can do an example here. Okay. So look, you leave $16,000 in an account for 5 years at an interest rate of 9%. It's compounded monthly. How much money will there be at the end of 5 years? Okay, well, let's label some of these pieces here. 16,000, that's what you're starting with, so that's your P. 5 years, I give it to you twice. That's the number of years, right? T. Here's your rate, R, but we got to make it a decimal. 9% is, move the decimal place twice, 0.09, or you could divide it by 100 to get 0.09. Then here's the one people have to think about, compounded monthly. Okay, how many times is it compounded in a year? How many months are there in a year? Good, somebody else said 12. 1 year I did this in a class, and everybody in the class told me 10. I had to go check a calendar just to make sure I wasn't losing my mind, because that is, that happens sometimes. I just go crazy, but no, it is 12. There are 12 months in a year. Okay, so let's see if we can put this all together. So what's our P? 16,000. 1 plus R is 0.09 over 12 to the, let's see, N is 12 times T is 5. Okay. And so all we're going to do here is use a calculator. I will go ahead and tell you may want to do this very carefully in pieces, using your calculator in pieces, because people tend to not put their parentheses, and they tend to, this 5, they don't put parentheses up here either. I'll go ahead and give you hints. If you're typing this in a calculator, you're going to want to put parentheses here. You're going to want to use these parentheses here. You might even want parentheses here. You got to be really careful so your calculator actually does this right. Calculators are dumb. You're the smart one. You have to make sure you tell it how you want this thing figured out. But if you put this in a calculator, you'll get, let's see. I think I've typed it in a calculator, and I believe that I missed a decimal place. So let me type this in my calculator again. So let's see. We'll go 16,000, 1, 2, 3, parenthesis, 1 plus parenthesis 0.09 divided by 12. Close one parenthesis, close the next parenthesis. And then we will need an exponent raised to the, and let's see, what is it, 12 times 5 in parentheses, not 12.5, I can't type times 5 in parentheses, equals, there we go. Yeah, I left a 0 off my answer. You will get 25,050 point, and I'll put a few decimal places, 896. 896. That's enough. Now, this is money. How many decimal places does our money have? 2, right? So we're going to need to round these answers to 2 decimal places. So $25,050. And this will be 90 cents. Because the 6 is above a 5, so it means we'll round this up. When we round that up to 10, that 1 carries over there. So there we go, $25,050.90. Okay? So you'll have one of those on the test. and on your work where you just plug into the formula. It's not meant to be stressful if you take your time and use those parentheses, okay? Awesome. That's all I have for you today. Make sure you try the problems. Make sure you're watching the videos. Email me if you have any questions. Y'all have a wonderful night.